In today's lesson, we're going to be looking at bond energy calculations. So we have two lesson objectives today. The first one is to explore the direction in energy flow when bonds are formed or broken. So we need to be examining or exploring which direction energy is flowing from a system, whether it's flowing into a system or flowing out of a system. The next learning objective is to calculate the overall energy change in a chemical reaction. So when we know the direction in which energy is flowing when bonds are broken or bonds are formed, then we need to make a calculation to give us the overall energy change in a chemical reaction. Before we start, we're just going to complete a few recap questions, and this will take approximately 10 minutes. Now, I would like you to answer your question on Teams, and can you number your questions, and at the heading of your answer sheet, can you put recap questions? So the first question, I want you to define the term activation energy. So one sentence defining the term activation energy. Question number 2, part A. When the reactants are at a higher energy level than the products, what type of reaction has taken place? So when the reactants are at a higher energy level than the products, what type of reaction took place? So you will need to refer back to on your notes, looking at the energy profile diagrams. Part B. What happens to the temperature of the surroundings? So following on from part A, you need to determine what type of reaction has taken place, whether it's endothermic or exothermic. And based on that answer, I want you to tell me what happens to the temperature of the surroundings. Question number 3. If a reaction is endothermic, explain the energy level position of the products and reactants. So you will have to refer back to the energy profile diagrams. So which one is higher? Which one is lower? So if a reaction is endothermic, explain the energy level positions of the products and reactants. Which one is higher and which one is lower? Question number 4. What is the unit of energy for products or reactants in reaction profile diagrams? What is the unit of energy for products or reactants in reaction profile diagrams or energy reaction profile diagrams? What is the unit that we are dealing with? Question number 5. What can lower the activation energy level? What can lower the activation energy level? A one-word answer is fine. So for this, so you have 5 questions. Can you write your answers on a Word document, or if you're typing it on Teams, make sure you number your questions clearly, and can you put recap questions and submit your answers onto Teams. I'll give you 10 minutes to think about this, and can you submit your answers onto Teams. When we are determining if a reaction is exothermic or endothermic, we are essentially looking at the formation or the breaking of bonds. And it's a combination of making and breaking bonds that give us the overall energy change in a reaction. So to determine if a chemical reaction is exothermic or endothermic, the balance between the energy needed to break the bonds and the energy released when new bonds are made must be calculated. And once we have that calculation, we can determine if a reaction is endothermic or exothermic. Now, in doing this, we can actually also work out the energy required to break a chemical bond or to form a chemical bond. Here you can see a simulation that is showing how bonds are broken. Look at the direction of the energy being supplied to the bonds. Notice that they are coming from the surroundings going into the bonds to break them. So this results, so energy is supplied to the bonds to break them, and this is coming from the surroundings. So let us define now the breaking of bonds between atoms in chemical reactions. So what we say is that in chemical reactions, energy must be supplied to break the bonds. So energy must be supplied to break the bonds in the reactants. So to break the bonds between atoms in the reactants. So there are a few key words here that I want you to think about. In chemical reactions, energy must be supplied. So that's very important. Energy must be supplied to break bonds between atoms in the reactants. So if energy is being supplied, energy is taken in from the surroundings to break the bonds. So as you can see to the simulation on the right, you are seeing here a water molecule, and energy is being taken into the bonds from the surroundings, and that is what is causing the bonds to break. So if we were to take a simple water molecule, to break the bond between oxygen and hydrogen, energy must be supplied or taken into the system of the bond, and that will break it. And this energy comes from the surroundings. Now, if energy is taken in from the surroundings, and you can see here in the simulation that energy is being supplied to the bonds to break them. So the bonds between the atoms are being broken by energy being supplied from the surroundings. So energy is going into the bonds to break them. Can you now type on Teams quickly to tell me what type of reaction this would be? Would it be exothermic or endothermic? So what type of reaction? So on the simulation, you can see energy going into the bonds from the surroundings. What type of reaction would this be? So if we were breaking bonds and energy is being supplied from the surroundings into the bond to break it, what type of reaction would this be? Now we're going to look at bonds being formed. You can see here in this simulation, for bonds to be formed, the energy is being released to the surroundings. And as the energy is being released to the surroundings, we get a new product being formed. When bonds are being formed, so when new bonds are formed between atoms in a chemical reaction, energy is released to the surroundings. So as you can see in this simulation with the water molecule again, we are seeing the formation of a water molecule. We can see that for the oxygen and the hydrogen atoms to bond together, energy is released out to the surroundings. You can see that the energy is coming out to the surroundings as they combine. So what we say is that when new bonds are formed between atoms, in a chemical reaction, energy is released. Energy is released to the surroundings. So take a look at the simulation again, and you can see how energy is being released to the surroundings as the new bonds are being formed. Now, this type of reaction, where energy is released to the surroundings, is an exothermic reaction. So can you just take this down? In forming bonds, when we form new chemical bonds between atoms, energy is released to the surroundings. Now let us define what bond energy is. The energy needed to break the bond between two atoms is called the bond energy for that bond. So we are going to be dealing with various types of bond energies, and you'll be given various values for bond energy. Now, bond energy is the energy needed to break the bond between two atoms. And the values you will be given in charts and tables will be the energy that is needed to break the bond. For any particular atom, or you need more than one atom. It could be the same type of atom, or it could be different types of atoms. But if the two atoms are bonded together, the bond energy refers to the energy needed to break the bond. Now, the unit of bond energy is kilojoule per mole. I'll repeat again. The unit of bond energy is kilojoules per mole. Your first task here for this particular part of the lesson for bond breaking, I want you to sketch out the axes here, and I want you to label the axes correctly, and I want you to tell me what type of reaction has occurred here. Look at this reaction profile carefully. This is for hydrogen. Now we've got H2 gas, and then we've also got hydrogen atoms existing separately. So looking at this energy profile diagram, I want you to tell me, first I want you to label the axes correctly, and then I want you to tell me what type of reaction has occurred, whether it's exothermic or endothermic. I would like you to do this in a Word document, or you can sketch the answer on a piece of paper and you can take a photo of it and send it over. But I need to have the axes labeled clearly, and you need to tell me what type of reaction has occurred. In addition to labeling the axes and telling me what type of reaction has occurred, I want you to label the products and the reactants clearly on your diagram as well. So I'll repeat again. You are to sketch this graph out. You are to label the axes correctly. You are to tell me what type of reaction has occurred, whether it's exothermic or endothermic. And then you are to also label the products and reactants correctly. So can you take 5 minutes and submit your answers back to me on Teams? Now we have another very important statement. This is that breaking and making a particular bond always involves the same amount of energy. So this statement is very important. What is being said is that breaking and making a particular bond always involves the same amount of energy. If that is the case, for this second task, and I'm going to give you 5 minutes again for this, I want you to draw an energy versus progress of reaction graph, just like you saw before, for the formation of hydrogen. So for the formation of hydrogen, I want you to draw an energy versus progress of reaction graph for the formation of hydrogen. The statement above will help you. Breaking and making a particular bond always involves the same amount of energy. Okay, now you must include the value of the energy released or absorbed. I'll give you a hint for this task here. Bond making, energy is released to the surroundings. Therefore, what type of reaction would it be? So you are to draw an energy versus progress of reaction graph for the formation of hydrogen, and you are to include the value of the energy that is released to the surroundings. So the graph has to be correctly drawn with the products and reactants correctly labeled, and the arrow in terms of if it's exothermic or endothermic also has to be correctly placed on the graph. So can you take 5 minutes and can you submit your answers back to me on Teams in the same manner as the previous task? Now here are some common bond energy values. And you can see here for various types of elements, when they're bonded to, even if it's the same element, for example carbon, if there's a bond between a carbon and a carbon atom, to break that bond, it requires 347 kilojoules per mole. If we have a bond between carbon and nitrogen, for example, it is 286 kilojoules per mole to break it. So these are various bond energies. I want you to take down these bond energies because you will need to use these later on for exam questions and other task questions. So I want you to copy down this table in your notes and make sure that you take it clearly, clearly identifying the bonds, whether it's a single bond or a double bond. And can you also make a note of the unit, kilojoules per mole, because this will also be very important later on. So can you take down both of these tables? I'll give you 5 minutes for this and then we'll move on. So can you pause the video here? Can you copy both tables? Make sure that you're correctly putting in the double bond or single bond or triple bond as required, and make sure that you take a note of the unit. Now remember, this is the energy required or needed to break the bonds. Now, how do we use these bond energies to actually calculate the energy change? So what we say is that to calculate the energy change for a chemical reaction, we must do two things. First, we must work out how much energy is needed to break the chemical bonds in the reactants. So we're talking about using the bond energy values in a chemical reaction to work out the overall energy change, to work out whether it's exothermic or endothermic. So we first have to break it down into parts. The first part is how much energy is needed to break the chemical bonds in the reactants. Then the second part is how much energy is released when the new bonds are formed to make the products. So I'll repeat that again. If you want to work out the overall energy change, the first step is to calculate how much energy is needed to break the chemical bonds in the reactants. Then once you've worked that out, then you calculate how much energy is released when the new bonds are formed in the products. So can you take down the steps for working out the energy change for a chemical reaction? These two steps. Now, we are going to use the values in the common bond energy tables. So in the two tables that were given, you are given common bond energy values. Using those values, you're going to answer these questions here. And I'm going to give you 15 minutes to do this. So for each question also, you need to state if the reaction is endothermic or exothermic. So you'll be typing this on a Word document and submitting it back to Teams. And can you put the subheading task 3 and then can you number the questions accordingly? You do not need to type out the questions, but you must put task 3 and number the questions accordingly. And for each question, you must state if the reaction is endothermic or exothermic. So the first question, how much energy is needed to break a hydrogen atom bonded to an oxygen atom? So how much energy is needed to break a hydrogen atom bonded to an oxygen atom? How much energy is needed to break it? And I want you to tell me that if it's exothermic or endothermic. Part B, how much energy is needed to form the carbon and nitrogen bond? So how much energy is needed to form the carbon to nitrogen bond? And then I want you to tell me, is that exothermic or endothermic? Part C, how much energy is needed to break the nitrogen bond? It's got a triple bond, and I want you to tell me how much energy is needed to break this nitrogen to nitrogen bond. And I also want you to tell me if it's exothermic or endothermic. The second question, part A, how much energy is required to break 3 moles of Cl2 molecular bonds? So how much energy is required to break 3 moles of Cl2 molecular bonds? Part B, how much energy is required to form 2 moles of oxygen? How much energy is required to form 2 moles of oxygen? Again, for each question, I want you to tell me if the reaction is exothermic or endothermic. Part 3. Breaking which bond cools the surroundings more? Carbon to oxygen, or hydrogen to oxygen. So breaking which bond, either the carbon to oxygen or the hydrogen to oxygen, cools the surrounding more? And I want you to explain your answer. So you're going to have to refer to your table and also to a sentence or definition that I gave you alongside the table. So breaking which bond cools the surrounding more? Carbon to oxygen or hydrogen to oxygen? And I want you to explain your answer. So you're going to have to think about that and construct your answer accordingly. Question 4. Put the following in order, the lowest first, of heating up the surroundings. So if the surroundings were to be heated up and we have a number of different chemical bonds, starting with the lowest one, so the lowest chemical bond which is broken, which heats up the surrounding for the formation. Sorry, let me just repeat that. You need to put the following in order, lowest first, of heating up the surroundings for formation. So when these bonds are formed, i.e. the nitrogen bond, the nitrogen to nitrogen, when that bond is formed, or when the carbon to carbon bond is formed, or when the carbon to oxygen bond is formed, which one of these is going to heat up the surroundings the least? And that's going to be your first one. And then you're going to list the bonds that are formed in order from the lowest to the highest in terms of heating up the surroundings, because this is formation. So you're going to have to refer to the table. So putting the following bonds that you're seeing here, you've got 1, 2, 3, 4, 5, 6 bonds that have been formed. Which one heats up the surrounding the least as the bond is formed? And then you're going to work your way up to where, when the bond is formed, whichever one it may be out of the 6, which one heats up the surroundings the most as it's being formed. So you're going to have to refer to the table to get your answer. Task 4. I want you to now go further with these calculations using the tables. Can you now answer these questions on a Word document using this table and the diagram on the right hand side to help you? Can you answer questions 1A, B, C, D and E and 2A, B, C, D and E? Use the tables here to help you and the diagrams on the right. Can you upload your answers on a Word document on Teams once you've finished? And I'll give you 15 minutes for this. This is task 4. You need to be familiar and comfortable with working with different types of bond energy calculations and looking at tables and being able to carry out the calculation. We have looked at how to calculate the energy for bonds being broken or bonds being formed. Now we're going to calculate overall energy changes. And to do this, we need to know how to define an overall energy change. So what we say is that the difference between the sum of the energy needed to break bonds in the reactants and the sum of the energy released when bonds in the products are formed is the overall energy change. So this is the difference between the sum of the energy needed to break the bonds in the reactants with the sum of the energy released when the bonds in the products are formed. And this is the overall energy change. We can put it simply as the overall energy change, delta H, is breaking bonds in the reactants minus forming bonds in the products. Another way to say it is energy taken in minus energy released. This gives us the overall energy change. So can you take down the definition and also the different ways in which you can put that in a shorter context in terms of an equation? So can you pause the video here and can you make sure that you have this description above and a shorter way in terms of how to actually put it into a simple equation that you're going to use later on. Now we're going to work through an example where we're forming ammonia. Now this is known as the Haber process and it's a reversible reaction. Now before we start calculating the overall energy change for the Ford reaction, I'm just going to recap here what we're actually looking at when we're talking about overall reactions. So in some reactions, the energy released when new bonds are formed, i.e. as the products are made, is more than the energy needed to break the bonds in the reactants. These type of reactions transfer energy to the surroundings, therefore they are exothermic. So I'll repeat again. In some reactions, the energy released when new bonds are formed, i.e. as the products are made, the energy released is more than the energy needed to break the bonds in the reactants. In these reactions transfer energy to the surroundings. They are exothermic reactions. However, you can also get other types of reactions where the energy needed to break the bonds in the reactants is more than the energy released when new bonds are formed. These reactions transfer energy from the surroundings to the reacting chemicals. Therefore, they are known as endothermic reactions. Now we are going to calculate the overall energy change for the Ford reaction for ammonia and determine whether it's an exothermic or endothermic reaction overall. So to do that, we need to now break down each step as we've looked at it in different parts and bring it all together. And we're going to do this for this reaction for the Haber process forming ammonia. The first step that we need to do is look at the balanced equation. So you must always have a balanced equation to work with. This is because you are going to deal with the number of moles. And if you remember back to your common bond energy table, you will notice that the unit of the bond energy is kilojoules per mole. So that's per single mole. That's what those values represent in the tables. That's why it's very important that when you start calculating overall energy change, you know that you have a fully balanced equation and it's correctly balanced. And in this equation, it is correctly balanced. So this equation tells us that the bonds in 1 mole of nitrogen and 3 moles of hydrogen need to break in the reaction. Because we're going for a Ford reaction to produce ammonia, from our reactant side, we need to break 1 mole of nitrogen bonds and 3 moles of hydrogen bonds need to be broken in this reaction first, because you need to break the bonds and then form bonds to form your ammonia, to form new product. And the equation is telling us that 1 mole of nitrogen and 3 moles of hydrogen need to break in the reaction. So looking at this in terms of bonds, what you will see here, you can see that the bonds have been indicated in red. So the nitrogen is a triple bond bonded with another nitrogen. And above it, you see how much energy is required to break that bond, for 945 kilojoules per mole. And then you see for hydrogen, you see the hydrogen to hydrogen bond there, and you see the equivalent number of, in terms of energy, that is required to break that bond, which is 436. And you can see that I've listed it 3 times because you have 3 moles of hydrogen. Therefore, you have 3 lots of it. Now, this means that the total energy of the bonds broken in the forward direction is, which is an endothermic process, because we need to take in energy from the surroundings to break these bonds. The total energy that is required is 2,253 kilojoules. So that's the total amount of energy that is needed to break the bonds in the forward direction. So can you just take this down? This is the first part, where we've identified the reactants, we've identified the number of moles, and then we've identified the bond values, the bond energy values to break these bonds, and we've totaled them, and it's given us 2,253 kilojoules to break these bonds in the forward direction. Now we have, once we've broken the bonds, we have 2 nitrogen atoms and 6 hydrogen atoms. So it is these atoms now which have been separated will form ammonia, NH3. And we still have to refer to the equation. That's why it's there at the top still. And see how many moles of ammonia are formed, which is 2. So I'll repeat again. Once we've broken the bonds in the reactants, we will have 2 nitrogen atoms and 6 hydrogen atoms. These atoms will combine to form our ammonia product, NH3. Now, we have 2 moles of ammonia. So these bonds are made in the forward direction. Again, it's the forward direction. So my question to you is, how many nitrogen to hydrogen bonds are there? How many nitrogen to hydrogen bonds are there? Can you just pause the video here and type your answer back on Teams? How many nitrogen to hydrogen bonds are there? What you should have got is that there are 6 nitrogen to hydrogen bonds. Okay, there are 6 nitrogen to hydrogen bonds. This is because you have 3 just in one ammonia molecule, but then you have 2 lots of it because you have 2 moles. So that means it doubles. So you have 6. 2 times 3 is 6. So there are 6 nitrogen to hydrogen bonds that are here. So these are the bonds that are made in the forward direction. So now we will use this piece of information where there are 6 moles of the nitrogen to hydrogen bonds that make up the forward reaction for producing ammonia. And again, as before, I've listed the bond energy values above the actual structural displayed formula that you have. So you've got your nitrogen to hydrogen atom bonds being displayed, and I've put 6 of them there. And I've also put the bond energy value from the table. Now, since I've put the bond energy value there, remember from our definition that whether you're breaking the bond or forming the bond, the energy value is the same. Okay, so if that's the case, we can still use the same value reading off the table of the chart, which is 391. That's why I've listed 391 above each nitrogen to hydrogen bond. So using this, we can say 6 times 391 will give us 2,346 kilojoules. So this is the energy that is transferred to the surroundings. Why? Because when you are forming bonds, you will transfer energy to the surroundings based on our definitions which we looked at previously. So what we say here is that 2,346 kilojoules of energy are transferred to the surroundings, which is an exothermic reaction. Now we have to put all the parts together to work out the overall energy change. And what we say is that breaking bonds in the reactants minus forming bonds in the products. So this gives us 2,253 joules, which we calculated for breaking the bonds in the products, minus 2,346 kilojoules that resulted when we formed the bonds in the products. So breaking the bonds in the reactants, we got 2,253 kilojoules, and forming bonds in the products, we have achieved 2,346 kilojoules. Following the equation through, you get minus 93 kilojoules. Now the minus value indicates that it is an exothermic reaction. That's what it is telling us. So therefore, when we talk about the energy, we say that minus 93 kilojoules is what we're left with. The minus value indicates to us that it is an exothermic reaction. We state the answer correctly by saying that 93 kilojoules of energy have been transferred to the surroundings in the forward reaction. So that's how we bring our answer down, and the minus value indicates that it is an exothermic reaction. Now, if you had to see this in terms of an energy and progress of reaction graph, you can see here how the energy, in terms of energy being absorbed to break the bonds and energy being released to form the products, how that can be graphically shown on your energy profile diagram. And what I want you to notice here is that because this is an exothermic reaction, the products must be lower than the reactants. And this is clearly represented here, that the products are at a lower energy level than the reactants, meaning that energy was released to the surroundings. And you can see 93 kilojoules of energy have been released to the surroundings. And you can see where the activation energy peak is as well. You can see that you've got 2 nitrogen atoms plus 6 hydrogen atoms will form together to form our ammonia. So you can see at each stage where the reaction has been progressing, and you can map this out back onto how we actually calculated this value. If you work it back through our example, you can see where these values fit in. So this breaks down what we've just calculated in a graphical form. And this diagram should be familiar to you because this is the energy profile diagram which we have been looking at so far. And you can see how we actually map the values and how we get this graph now. You should be able to see how we get this shape of graph. Now we're going to look at some exam questions. and I would like you to complete this on a Word document and upload your answers on Teams. So I'm going to cycle through a number of exam questions now. So I'm going to show you the exam questions, then I want you to go back and pause at each section, complete your work on a Word document and upload it back to me on Teams. So here you're just going to have, for this exam question, you're going to have to look at a reaction, an energy profile diagram, and I want you to answer these multiple choice questions here. In this question, you are going to have to calculate the bond energy for a particular type of bond using the information given in the table and the equation. And here you're required to calculate the overall energy change for the reaction based on the information given.